Last class we learned the OSI model and A2A2S dual, the 7-layer map that lets us reason about any network. Today, we meet its practical cousin, the model that the real internet actually runs on, the TCP/IP model. Here is the situation that confuses newcomers. There are two models, not one. OSI has 7 layers and is the perfect teaching tool, and A200 to handle a clean, fine-grained map. But the internet was not built on OSI, it was built on TCP/IP, a leaner model with just 4 layers. Now both describe the same journey a message takes, just at different levels of detail. And a good networker keeps both in their head, and A200 file OSI to reason and troubleshoot, TCP/IP to describe what is really happening. So today, we will learn the 4 TCP/IP layers, see exactly how they map onto the 7 you already know, and revisit encapsulation and A212, how your data gets wrapped up to travel and unwrapped to arrive. Let us learn the model that quietly powers everything. Here is what we will understand today. First, why we need a second model at all. Second, the 4 layers of TCP/IP. Third, the lower pair and A212, link and internet. Fourth, the upper pair and A202, transport and application. Fifth, how TCP/IP maps onto OSI. And sixth, encapsulation in action across the stack. Let us begin. Let us start by clearing up the natural confusion of having 2 models. The OSI model, which we studied last class, is the teaching map. Its 7 layers give us a precise, shared vocabulary for reasoning about networks and for pinning down exactly where a problem lives. It is superb for understanding an A212. But here is the twist. The internet was never actually built on it. OSI is largely a reference model, a way of thinking. The internet actually runs on the TCP/IP model and AT12, OLHA, a leaner, more practical stack of just 4 layers. When real data crosses real networks, it is TCP/IP that is doing the work. It is named after its 2 most important protocols, TCP and IP, and it is the model that engineers building and running networks reach for every day. So think of it as 2 views of the same thing. OSI is the detailed anatomy diagram in the textbook. TCP/IP is the working machine on the workshop floor. They do not contradict each other, and A2 files question tiles. TCP/IP simply groups some of OSI and 39 layers together into a more compact, practical set. Knowing both means you can reason with OSI and 39's precision and speak about the real world with TCP/IP and 39's accuracy. So the takeaway, OSI is the teaching map, but the internet actually runs on the TCP/IP model, an AT112, a leaner, practical stack of 4 layers, an AT112. So you keep OSI for reasoning and TCP/IP for describing reality. Let us meet the 4 layers from the top down and I212. The same direction data travels when you send it. At the top is the application layer. This is where the protocols your programs speak live and AT towards the web, email, file transfer, the domain name system. It is closest to you, the user. Below it is the transport layer. This is home to TCP and UDP, and its job is end-to-end delivery in A212, getting the whole message reliably or quickly from one program to another. Then comes the internet layer, where IP lives. It handles addressing and routing and A212, giving every device an IP address and getting packets across network after network to reach anywhere in the world. And at the bottom is the link layer, which handles the actual local hop, moving the data across one physical connection to the next device over the wire or the air. Application, transport, internet, link, and 812 4 layers, and everyone has a clear job. So the takeaway, TCP/IP has 4 layers and 821.2 application at the top for app protocols, transport for end-to-end delivery, internet for IP addressing and routing, and link at the bottom for the local physical hop. Let us look more closely at the bottom pair, because together They solve the problem of getting data from your device all the way across the world. The link layer handles the local hop. Its job is to move data across a single physical connection, an 80 or 12, from your laptop to your router, or from one router to the next along the path. It deals with the actual medium, the cable, the Wi-Fi, the hardware addresses that identify devices on that one local link. It gets you exactly one step forward. This layer rows together what OSI split into the physical and data link layers. The internet layer takes over for the long journey. This is where IP lives, and its job is addressing and routing, giving every device a logical IP address and letting routers forward packets from one network to the next until they reach the destination. Where the link layer moves you one hop, the internet layer strings those hops together into a path that can cross the entire globe. Together they are a beautiful division of labor. The internet layer plans the whole route and labels each packet with where it must ultimately go, while the link layer actually carries it across each individual step of that route. Neither could reach the world alone. Combined, they do. So the takeaway, the link layer moves data across one local physical hop, while the internet layer adds IP addresses and routing to cross many networks and 80-100 to solve. The link layer takes each step. The internet layer plans the whole journey. Now, the upper pair, which sits closest to your software and makes the raw delivery actually useful. The transport layer is where TCP and UDP live, and its job is end-to-end delivery between programs. Remember from the OSI class, TCP delivers reliably, checking that everything arrived in order, while UDP delivers fast, without the guarantees. The transport layer is what makes sure the data does not just reach the right machine, but the right program on it in the right condition. The application layer sits on top and is the one you actually interact with. It is not the app itself, but the networking protocols the app speaks, and 80-112. The protocol behind your web browser, the one behind email, the domain name system. That turns names into addresses. When you load a website, you are using an application layer protocol, riding on transport, riding on internet, riding on link. Notice the elegant stacking. The application layer just says what it wants to send. Transport makes sure it arrives correctly. Internet gets it to the right machine anywhere. Link carries each physical step. Each layer trusts the one below and serves the one above, and 80-112. Exactly the layer thinking from last class, now in 4 practical tiers. So the takeaway, the transport layer delivers end-to-end with TCP or UDP, and the application layer is the protocols your programs actually speak, like the web, email, and DNS NAT2 the top 2 layers that turn raw delivery into useful communication. Now let us put the 2 models side by side, because seeing how they relate makes both clearer. TCP/IP has 4 practical layers, and it describes how the internet really works, and 80-112. It is the model in the engine room, matched to real protocols and real implementations. It is compact because it bundles related concerns together. OSI has 7 teaching layers, and it offers a finer grain map for understanding and for troubleshooting with precision. Its extra layers give you more specific places to point when you are diagnosing a problem or explaining a concept. But here is the key insight. They are not rival descriptions of different things. They describe the very same journey your data takes, just at different levels of detail. TCP/IP simply groups several of OSI and IN39 S layers into one, so nothing in OSI is missing from TCP/IP and 8112. It is just folded together. Once you see that, the 2 models stop competing in your mind and start reinforcing each other. So the takeaway, TCP/IP and T79, S4 layers, and OSI and T7 describe the same journey at different granularity and 8112. TCP/IP groups OSI and T79. So the 2 reinforce rather than compact practical model. Let us make the mapping exact, because knowing precisely which TCP/IP layer covers which OSI layers is genuinely useful in interviews and in practice. The TCP/IP application layer covers OSI layers 7, 6, and 5 and 8200, application, presentation, and session all rolled into one. TCP/IP decided those three concerns could sit together. So what OSI splits three ways. TCP/IP handles as a single top layer. In the middle, it is one-to-one and easy. The TCP/IP transport layer is exactly OSI layer 4, and the TCP/IP internet layer is exactly OSI layer 3. These two line up cleanly, which is why TCP and IP map so neatly onto transport and network. And at the bottom, the TCP/IP link layer covers OSI layers 2 and 1 and A212, data link and physical together. TCP/IP treats getting bits across the local connection as one combined job. So the full picture, top 3 of OSI become application, the middle 2 map 1-to-1, and the bottom 2 become link. 4 layers, 7 layers, perfectly reconciled. So the takeaway? The mapping is application over OSI 5 and ATA 7, transport equal to OSI 4, internet equal to OSI 3, and link over OSI AN AAA, 2 OSI AN ATADAN, 2A ATAT curve. The top and bottom are grouped, the middle lines up 1-to-1. Encapsulation, which we met with OSI, works exactly the same way in TCP/IP and A292 half, and seeing it once more, in 4 layers, cements the idea for good. It begins with your data at the application layer and A212. The actual message, the web request, the email you are sending. That is the payload, everything else exists to carry. As that data travels down through the layers, each one drops it in its own header. Transport adds a header identifying the program and whether it is TCP or UDP. Internet adds a header with the source and destination IP addresses. Link adds a header with the local hardware addresses. Each layer packages what it received from above, like nesting the message in one envelope after another. By the time it reaches the bottom, it is a stream of bits on the wire in A212, and on the receiving machine, the whole thing runs in reverse. Each layer reads and strips off its own header, passing the rest upward until the original data emerges cleanly at the application layer for the receiving program. Wrap going down, unwrap going up, through 4 layers instead of 7, but the identical principle. So the takeaway, as data goes down the 4 TCP/IP layers, each adds its own header and A212s, encapsulation and A212s, and the receiver peels each header off on the way up, so the exact original message arrives at the top, just as in OSI. It is worth understanding why, of the 2 models, TCP/IP became the one the whole world actually uses and 82 hull for, because the story carries a good engineering lesson. TCP/IP won for a simple reason. It was simple, open, and actually built. While OSI was being carefully designed by committee as a grand reference, TCP/IP was already running on real networks and A212, working code, freely available, connecting real machines. It was pragmatic and available when people needed to build things, and being open meant anyone could implement it without permission or fees. OSI, for all its elegance, largely stayed a reference model, and A22 tool, enormously influential as a teaching tool and a shared vocabulary, but never the thing the internet was actually assembled from. The finest design does not win if the working available alternative gets there first, and people build on it. There is a lesson in that worth carrying beyond networking. Real shipped, open solutions tend to win over perfect designs that arrive late. The internet chose the model it could actually use today, and that choice compounded as everything got built on top of it. So the takeaway, TCP/IP became the standard because it was simple, open, and actually implemented and running, while OSI remained mostly a reference, A212, a reminder that a working available solution usually beats a more perfect one that ships too late. Let us close with the practical habit and 82 tool. How to actually carry 2 models in your head without confusion. Use OSI to reason and troubleshoot. When you are diagnosing a problem or explaining a concept, its 7 fine-grained layers give you precise language, Is this a layer 2 issue or a layer 3 issue? Its detail is exactly what you want when thinking carefully, step by step. Use TCP/IP to describe what real networks actually do. When you are talking about genuine protocols and real implementations, the 4-layer model matches reality and 8212. It is the vocabulary of the working internet, of the tools and systems you will actually operate. And across both, keep encapsulation firmly in mind. Headers are either going down the stack and peeled off going up, whether you count 4 layers or 7. That single mechanism explains how data really moves, and it is identical in both models. Hold OSI for precision, TCP/IP for reality, and encapsulation as the engine under both. So the takeaway? Reason and troubleshoot with OSI-NT9, 7 layers. Describe real networks with TCP/IP, PNT9, 704, and keep encapsulation in mind for both N8222. Two complementary models and one shared mechanism give you a complete, practical picture. Let us gather the whole class in one breath. TCP/IP is the practical model the internet actually runs on. It has 4 layers: N8212, application, transport, internet, and link. Link and internet handle the local hop and then IP routing across networks. Transport and application give end-to-end delivery, and then the protocols your apps speak. It maps onto OSI and N8112, 4 layers grouping the same 7, describing one journey. And encapsulation wraps data in headers, going down, and peels them off, going up. Next class, N8112, IP addresses up close, their structure and how they are organized. One idea at a time. That is the TCP/IP model and 80/24, the 4-layer stack that quietly carries every message on the internet, mapped cleanly onto the 7 OSI layers you already knew. 2 models, 1 journey, and encapsulation as the shared engine that wraps your data to travel and unwraps it to arrive. Hold both in your head, and network diagrams, protocols, and troubleshooting all fall into place. We will see you in the next class.